Okay, we actually took data from a video of water flowing out of the tube, the project situation. We just had a cylindrical container, or the cylindrical section of a large soft drink container with a tube sticking out of it. We let water flow out of that tube, and we measured the times at which depths took different values, and we'd have that video. And you could verify these values. We found that when the counter, we used a mouse to stop the video when we thought the water hit each mark, and we got these times at which the depths had these values. Now, what we want is we want a quadratic y equals at squared plus bt plus c model of this data. How do we do this? Well, we can write down the equations. Just plugging these values into this equation. And we do that for every pair of values, and we get 6 equations. And then we're going to get a matrix equation corresponding to that, much like the matrix equation I've written here, except I left a row out, and I tried to do these squares in my head, which I could do in a good day, but this wasn't a good day. So I don't think these are very accurate at all. On the whole, they really don't even make a whole lot of sense. Okay, anyhow. That should certainly be over 50,000, for example. We get something, though, that looks like this. Now, this is a matrix equation of the form AX equals B. So here's the matrix A, here's X, and here's B. The only unknown here is this X column vector. So we want to try to solve this equation for this X. However, we expect that if we did a row reduction on this A matrix, it would reduce to this. We'd have a 1, 0, 0, a 0, 1, 0, 0, 0, 1, then we'd be done. Everything else would be zeros down below that, because if these first 3 are like this, everything else is going to get wiped out. It would be highly unlikely that this wouldn't reduce to that this top 3 rows wouldn't reduce to the identity unless you had the same t value for 2 different points. Just because this is real world data is not likely to give you numbers that match up well enough to make a determinant 0. And so the determinant of this, you wouldn't expect the determinant of the first 3 rows of this matrix to be 0. For those reasons, you expect that A would reduce to this. Okay, well, let's put this into the picture of the basic subspaces, 4 basic subspaces. Okay, again, we have AX equals B. Okay, we've defined the mapping T of V equals AV. That mapping runs from what space to what space, if we use just real Euclidean spaces. Well, this matrix acts on vectors of length 3. That's because the rows, well, there are 3 columns. There are 3 numbers in each row to match up with the numbers in this column vector. So there have to be 3 numbers in the column vector. That means that X here has to be in R3. So since, well, that's going to make the first space R3. The second space, if I'd have written all the rows down, or the rows for all the equations, would have given me a row of, or a column of 6 numbers, which means that this is in R6. Okay, so we're mapping R3 to R6 if we define our transformation as being the product of A with the vector V. Okay, again, 3 numbers in a row means that A can only act on vectors in R3. And the fact that we have 6 rows means that the result is going to have 6 numbers in the column. Okay, so it's going to be in R6. Okay, now there's a notation that I invented. I mean, it wasn't a great invention or anything. this is the row space of A. Now, I didn't invent that. Over here is the range of the matrix A. Okay, so everything in this space gets mapped into this subspace of W, okay, of R6. And this subspace is called the range of A. R of A means range of A, not row space, but range of A. And that would be very easy to confuse if I didn't have a notation for the row space of A. Your text doesn't have a notation for that. Actually, it does. It uses the range of A transpose, but I don't even want to think of A transpose as mapping back here. It does, but you end up confusing subspaces if you think of that. So I'm not going to think in that term, although others might well, and I don't have any quarrel with that. Okay, so the notation that I invented for the row space, well, first of all, can you read this nursery rhyme? Well, if you read this properly, this thing here that kind of looks like a P, but it's just one symbol. It can be written in one stroke instead of like this. Okay? This is the Greek letter that makes sense of this. Row, row, row your boat. This is row. You don't want to read this as P, not if you want to get in my boat. I'm going to use this notation, row of A. Now I use row because it kind of corresponds to the letter R for range. It's just coincidental and unintended that it's read row, so row of A is the row space of A. That's kind of almost a pun between alphabets, which I didn't intend. I didn't choose row because it sounds like R-O-W. Incidentally, it's not spelled R-O-W, it's R-H-O. Okay. So this is the row space of A. And we've seen that you can, the rank of a matrix is the dimension of the row space, which is the number of non-zero rows you get when you completely reduce the matrix. You get the null space. And we have verified for a number of matrices that the null space you get for matrix and the row space are orthogonal. Not only are they orthogonal, but the dimension of the row space and the dimension of the null space add up to the dimension of the space. You'd say rank plus nullity equals n, where n is the dimension of the space. Okay? And this is dimension of row space. That's what we mean by the rank. And it's the number of rows you end up with, non-zero rows you end up with when you reduce. And this is the dimension of the null space. And the null space consists of all the solutions where the matrix times your column vector end up being zero. It's all the solutions here that you get if you map to zero. These are all ideas that we've seen and we should be comfortable with. So we have the row space of A, we have the null space, and if, as is the case, I guarantee it, this matrix reduces this way, the dimension of the row space is 3, and the dimension of the space is 3, so the null space has to have dimension 0, since these two dimensions have to add up to the 3, the dimension of the space. Over here, we have R6. Okay, we have the range of A, okay, the set of all vectors that you get mapping from here to here, That's also equal to the column space of A, and we've seen this, we know this. If we don't know it, we need to be sure we do. We review it, make sure we understand what the column space is and how we get it. And that's equal to the row space of A transpose for a very simple reason. And the reason is that the columns of A are the rows of A transpose. So that's it. So the column space is the row space of A transpose. So we have this, which is the row space of A transpose, also the range of A, also what we call the column space. We have the null space of A transpose then, because, I mean, A transpose, it makes a perfectly good mapping. I don't want to think of that as mapping back this way, because it then starts to look like an inverse mapping, and it usually isn't, seldom is. So if we map by A transpose, if we take this space and map by A transpose, we get some other space over here. It'll have its own row space and null space. And this will then be the row space of this mapping. Okay, well this then is, again, the row space of A transpose, and when we've established that this is the row space of A transpose, meaning that this has to be the null space of A transpose. If it's not in the row space, it maps to 0. And there we have it. So now we have our 4 basic subspaces, and we want to conceive of this problem in terms of those subspaces, because what comes out of this is not an invertible matrix. And it's got more rows than columns, so there's no reason to expect that you can find an A, B, and a C that satisfy this equation. And then it becomes a matter of finding the A, B, and C that comes as close as possible to satisfying this equation. And that'll be the vector x, that AX maps as close as possible to this vector. And as close as possible means, well, we have to talk a little bit more about what this means, but the direct sum and so forth. It's an orthogonal projection. If we were to project the x, well, if we were to project the B vector onto the row space, this projection would give us the vector in the row space that's as close as possible to the B vector. Because how close is this? It's this close. Any other vector, let's say this one, would only be this close, and this vector is longer than this one, and so is any other vector that you get from any other point in the row space. Now, you might understand that and you might not, but that's kind of the idea that we want to develop.